Yo, yo, yo. Welcome back. We'll be covering section 2 this episode. Section 2. Units or dimensional analysis. So, as far as classical mechanics is concerned, there's basically 3 units. Okay? We've got mass, length, and time. So everything is something like this. And I'll write maybe X, Y, Z, right? Everything can be written in terms of m to the x times l to the y times time to the z, right? Every unit. Take speed, for example. Speed is meters per second, or distance over time, right? That's going to be m to the 0, l to the 1, and time to the minus 1. The units of our answer is always going to be something that looks like this. So our answer, so you always get a good idea of what your answer is before you even have to do the problem, right? You know that our answer is gonna have something of this form times a numerical factor. So as I said from episode 1, if you check the units after you solve a problem, you know if your answer is wrong. If your answer doesn't match the units, you're wrong. If it does, well, you could still be wrong, but at least you have a shot at being right. So now we're going to do a couple of examples, and you're not expected to know how to do these problems yet, because we're going to discuss how to do them later. In future episodes, but let's see how far we can get with just dimensional analysis. So the book has an interesting notation where if it puts brackets around a quantity, like speed, then it's we're drawing just the units from this, right? So for example, the unit, so this means the units of speed, and I went with lowercase letters here, but it goes with, we'll use capital letters because the book goes with capital letters. So this, for example, would be length over time. Okay. Another example: the units of the gravitational constant G is L cubed over m times squared. Now you can find this out. So we know that where do we see the gravitational constant? We see the gravitational constant in the gravitational force between two masses. That's Newton's law of gravity, right? So that F equals G times m1 m2 over r squared. Now, so the units of F are newtons. You know, F equals ma, which means that the units of F are kilogram or mass times acceleration. So m, and then a we know is distance over time squared, right? So that's the units of F. So what we'll do now is we'll rearrange this equation, right? So I'll say G is F r squared over m1 times m2. Now, if we want the units of G, this is going to be ml over t squared, r squared, that's L squared, and then m squared, right? So it looks like this is the units of G is L cubed. One of these m's is gone, and that's going to be mt squared. Okay? L cubed over mt squared. Okay. Now, let's do an example. Example, pendulum. again, this is an example, so I don't expect you to be able to do this on your own right now. If you wanted to go for it, go for it. So let's do it together now. So we're going to approach this problem with just dimensional analysis, right? What do we know? What do we have here? We have mass m. We have a string of length L. And it swings back and forth, okay? The acceleration due to gravity is g. What can we say about the frequency? So frequency, what units do frequency come in, right? Frequency comes in hertz, but what's a hertz? It's 1 over time, right? So the units of frequency come in t to the minus 1, okay, or 1 over t, whatever. So how can we rearrange this to get 1 over t, right? So in other words, we have m to the x, L to the y, and g to the z. This needs to equal 1 over time. So the units of this, right? The units of this are going to be, so in other words, so m to the x, right? L to the y. And then g is acceleration. That's going to be L over t squared to the z. This needs to equal t to the minus 1. So here we have t to the minus 1 like this. And then m to the 0 and also L to the 0. So x equals 0. And then for L, if we multiply these two, you have L to the y plus z equals L to the 0. And then you have, so you can write m to the x equals m to the 0. And then you have t to the minus 2 z equals t to the minus 1, right? So x equals 0, right? What the heck? X equals 0. Y plus z equals 0. And then negative 2z equals negative 1. Z equals a half. Plug that back into here. Y equals negative z. So y equals negative a half. So our answer here is going to be, m to the 0, L to the negative a half, and g to the positive a half, g over L, to the 1/2. Okay, square root of g over L. This would be our frequency, right? So this is close, right? But the reason it's not quite it is because we didn't pay any attention to the initial angle, right? The initial angle. So it's a pendulum, right? Like this, mass m, L. It has some initial angle. It depends on this initial angle, right? So really the frequency would be something like this. And we didn't consider this because this is dimensionless, so it's impossible really to consider it. But we got really close, huh? To continue with this example, what about the energy, huh? What can we say about the total energy? So what is the energy, the total energy of the pendulum? Yeah, so what do we say about the what do we think the energy is? So I would like for you to pause it and try this on your own now. Now I'll provide a hint. You're going to want to do what we did over here, right? So maybe you're not sure what the units are for energy. Well, energy is also equal to work, and work is equal to, force times distance. So the units of energy must come in force times distance, right? So the units of energy must be force, that's mass times acceleration. So mass times L over t squared times distance, right? So these are the units of energy. Right, so knowing this, let's see if you can continue the rest of the solution on your own. Now let's do a walkthrough of how to solve this. And if at any point you were stuck when trying to solve this on your own and we uncover a step that unblocks you, please pause the video and try to do the rest on your own. Okay, so we're going to do what we did last time, which is, what we did last time is essentially this, right? So we're gonna rewrite this. So m to the x L to the y and L over t squared to the z. This should equal ml squared over t squared, right? So that's going to be m to the 1 L squared and t to the minus 2. Now, we're going to rewrite this, so it's m to the x L y plus z and t to the minus 2z. That equals m to the 1 L squared t to the minus 2. So it looks like x equals 1, y plus z equals 2, and negative 2z equals negative 2. So we have our x. Let's find z here. Z is positive 1, and then y equals 2 minus z. That means y equals 2 minus 1. That means y is also 1. So it looks like they're all 1. So when it comes to MGL, raising each one to the first power gives you MGL, right? So again, this is pretty close, right? The actual total energy is MGL times 1 minus cosine theta. Notice again that we were correct about our NGL, and all we were missing was a multiplicative factor of a function involving, this should be theta naught, involving theta naught, right? And that's because, again, we have no way of really doing this with pure dimensional analysis because this doesn't have any dimensions. Alright, so we have this example spring here. Spring. Alright, so go ahead and try this example on your own. I know that's an example and usually we don't do that, but I think that since we just did an example that's pretty much just like this one, I think there's potential for you to do it on your own. So pause the video now and try it on your own. Okay, if you got stuck, here's a hint. K, the units of K comes in these units, mass over time squared. I got that because we know that F equals negative kx, and if rearranging, we have that K equals negative F over x. F comes in mass times acceleration. So here's mass, m, times acceleration, L over t squared. And x comes in length. So the lengths divide out, and we have mass over time squared. So hopefully that helps. Okay, now let's do a walkthrough of the solution. So here are our known values. We have the force. So again, we're dealing with frequency, right? So we need some combination of k, x, and m to give us frequency, yeah? K is negative f over x, okay? And the dimensions of k then should be the dimensions of f, which is newtons, which is mass times mass times acceleration, which means that it's going to be mass times acceleration, and then we have an L down here, right? So actually, k is m over t squared. Okay, so now it looks like if we want frequency, then we're going to need m over t squared to the x power. This times m to the y power times position, L to the z power. We're going to need that to be, again, 1 over time. So I'll write t to the minus 1 power. Okay, so this says that if we multiply these two m's together, this is m to the x plus y. This is going to be t to the minus 2x. And this is L to the z. This is t to the minus 1. So t to the minus, and then of course m to the 0 and L to the 0, right? So x plus y equals 0. Negative 2x equals negative 1. And z is 0. Okay. So negative 2x equals negative 1. That means x is a half. And then y equals a negative x. So y equals a negative a half, right? So going back to this, we see that this was k, right? So we have k to the half, and then we had y was minus a half, so that's m. And then we had that z is 0, so there's no x dependency. And this is k to the 1/2 over m to the 1/2, which is the square root of k over m. So I think that's the frequency, right? All right. So now again, I would like you to find what the total energy might be from purely dimensional analysis. The dimensions of E are going to be it's going to be force times distance. Force being mass per mass times acceleration, and then distance, right? So we need our km and position. So k being this guy, m over t squared. m is just m to the y, and then L to the Z, we need that to equal m to the 1, L squared, and t to the minus 2. So we're going to combine again. We're going to combine these m's, and we have m to the x plus y, t to the minus 2x, and L to the Z. So looks like x plus y should be 1. Negative 2x should be negative 2. And z should be 2. Okay. That means that x should be 1. And y equals 1 minus x, which means y equals 0. Which means that our answer should look like k to the x power, that's just 1, and mass, which is 0, and then position, which is x, but z was 2, right? So our total energy should be something that looks kind of like this, kx squared. Okay, another example. Low orbit satellite. So what do we have here? We have m. We want to know what can we determine about its speed, right? All right, so I'll let you pause and try and figure it out on your own. All right, and now I'll provide a hint. So you might be thinking, how are we going to get v when v has dimensions length over time, and all we're given is mass? Well, true. That's all we're given. But we have something, we have a satellite, right? And satellites involve gravity. So G is involved. Okay. And not only that, okay, so that's fine. But that's not enough to get us there, because there's no way we can manipulate G to get length over time when the units of G are acceleration. So we need to so if we want L over T, we're going to need something that gives us L, or something that gives us T, so that way we can remove a T from the denominator, or by increasing the power of this L to an L squared and then taking the square root, right? So yeah, that's in fact what we're going to do is we're going to introduce a length by providing by taking for granted that we already know the radius of the Earth. This is a known fact, right? So even though it wasn't given to us, because it's a known thing, we can incorporate it. So there's your hint. Good luck. Okay, now let's do a walkthrough of this example. So our quantities are m, mass of the satellite, radius of the Earth, and acceleration due to gravity, right? So mass of the satellite, radius of the Earth, so that's going to be L, and acceleration due to gravity. This should come in L to the 1, T to the minus 1. So, this will stay that way. And here we have L times L to the Y times L to the Z. That's L to the Y plus Z. And then we have T to the minus twice Z. This is L to the 1, T to the minus 1. So, looks like, and this is, if you want, you can write this. And so X is 0. And Y plus Z is 1. And minus twice Z equals negative 1. Okay, so X is 0. Okay, and then it looks like Z is positive a half. So Y is 1 minus Z. That's going to be 1 minus a half. That means Y is also a half. So, going back to this, it looks like our M is M to the 0, so there's no M. And then it looks like the radius of the Earth is going to be, usually I put a capital E, is going to be raised to the 1/2 power. And it looks like G is going to also be raised to the 1/2 power. So this is going to be the square root of G times the radius of the Earth. And actually, this turns out to be exactly the right answer. Incidentally, right? But it could have been off by a factor, right? That's all I have to say in terms of the lecture for this section. Now we're going to jump into problems. So let's do problem 1.1. Escape velocity. Alright, so I'll give you all a chance to pause here and try and solve it on your own. Alright, so now I will provide a hint. And really this hint is kind of an elaboration on what they mean by this second statement here. So they say, use the fact that this, right? This implies that the acceleration doesn't depend on its mass, right? Which means that the overall motion doesn't depend on its mass, right? So, okay, so we want to show that this, right? 2g me over r. And basically the question is, how would I know, using purely dimensional analysis, to use m, the mass of the Earth, and not the mass of the object that's escaping Earth's orbit? You know this because the acceleration, and therefore the motion of the object, doesn't depend on the mass of the object. And we know this because the force between two objects equals this, which means that the force between the gravitational force between an object escaping Earth and the Earth is going to equal this, right? The mass of whatever that object is times the mass of the Earth over the distance between that object that's escaping and the center of the Earth. This is going to equal mg. Okay? And so you see that these m's cancel, and we see now that the acceleration doesn't depend on the mass of that object. It only depends on the mass of the Earth. So that's how you know not that you don't need to use the mass of the object. Okay? So that means the only properties, or sorry, the only values that we'll be using should be g, the radius of the Earth, Okay, we can call this E here. And the mass of the Earth. So let's use these, right? So that's your hint. Go forth from there. All right, now let's do a walkthrough of the solution. So G, the units of G are, as we found earlier, L cubed over mt squared. All right, so let's use that, okay? So we have L cubed over mt squared. This raised to the x power. Radius of the Earth raised to the y power. And the mass of the Earth raised to the z power. This should equal the units of velocity, which is length over time. All right. So this says L to the this is L cubed to the x times L to the y. That's going to be L to the 3x plus y. This is going to be m to the minus x times m to the z. That's minus x. That's m to the minus x plus z. And then here we have a t to the minus twice x. This is going to be L to the 1, t to the minus 1. So we see that 3x plus y equals 1. And we see that negative x plus z equals 0. And we see that negative twice x, equals negative 1. So, looks like x is a half. Okay. And also, looks like z is x. So that means z is also a half. And 3 times a half plus y equals 1. Which means y, well, I'll say 3 halves plus y equals 1. Which means y equals, 2 halves minus 3 halves. That means y equals negative 1 half. So going back to this, it looks like our big G gets raised to a half. Looks like our radius of the Earth gets raised to a negative half. So you can put that down here. And then looks like our mass of Earth gets raised to a half. So this says square root of g me over r. And there's a factor of 2, which we didn't know about, but there was no way for us to know about that. So, yeah. So we said apart from numerical factors, so we should be fine. Moving on. Problem 1.5. Damping. Okay. So I'll give you an opportunity here to pause and attempt this on your own. All right. So now let's do a hint. So it's really not different than the problems we've been doing, but now we have this n term that we're dealing with, right? And I mean, you just treat it as any other number, and it should be all right. But so I won't really discuss this part. I want to talk about the second part. After A and B, we're asked to see if our answers make sense, right? So for part A, look at the relationship between t, the stopping time, and your other variables, and do that for n equals 0, 1, and 2, and 3 if you want, and for n going up and up, right? Does a stopping time, think about conceptually what we're dealing with here. We're dealing with dampening, right? So this is what this means is, if you're not familiar with damping or the concept of damping, when you have a harmonic oscillator or any oscillator, and there's some kind of friction or resistance going on that depends on the velocity, then you know that oscillator is going to slow down until it comes to a stop. So your stopping time is how long it takes for your oscillator to go to a stop. And that depends on its initial velocity, right? And its mass and this constant b. So think about increasing and decreasing those values, mass and initial velocity, and see if it makes sense for the stopping time to increase or decrease with the changes in those values. Okay, so I'll let you pause and think about that and see if that helps. Okay, now let's do a walkthrough of the solution. So, like I said, in the hint, we're gonna do this the way we've always been doing it, right? So we know we have a mass m, and so the units of m are just mass. We have an initial speed v, the units of which are length over time, and we have this constant b. So we know that there's a damping force, F equals bv to the n, which means that b is equal to F over v to the n, which means that the units of b are the units of F. That's going to be mass times acceleration, so mass times acceleration. And then the reciprocal of speed is, instead of length over time, time over length. And of course we have an n here. I wrote time over time. Time over length, and of course we have an n here. So this can be simplified. This L to the n causes that 1 here to be subtracted by n, right? So we have m L 1 minus n. This square here causes this n to be subtracted by 2. Okay? That's the units of b. Now, so we'll say that the stopping time should be some combination like this. M, initial speed, and b. And so we'll say m to the x, L over time to the y, and then ml to the 1 minus n, t to the n minus 2 to the z. This should equal time, the units of time, which is m to the 0, L to the 0, and t to the 1. Okay. So we'll combine things to match, to make it look like this, right? So m to the x times m to the z is m to the x plus z. L to the y times L to the 1 minus n to the z. This is L to the y plus z times 1 minus n. Right? Because z, when you take a base to an exponent and raise that to an exponent, you just multiply the two exponents. Right? So we're just multiplying the two exponents. And then we do for that for t, right? So t to the minus y plus z times n minus 2. Okay? So x plus z equals 0. Let's write x equals negative z. Y plus z times 1 minus n equals 0. And negative y plus z times n minus 2. That equals 1. Cool. So what I'm going to do now is I'm going to take this equation and add it with this equation, right? So we have y minus y, that's 0. Z to the z times 1 minus n plus z times n minus 2 equals 0 plus 1, that's 1. And now I'll distribute this z, so z minus zn plus zn minus twice z equals 1. Negative zn cancels with positive zn. Z minus 2z is negative z equals 1. That means z equals negative 1. All right. Now that we have z, we immediately know that x is 1. And we can plug negative 1 into any one of these equations to get y. So y plus negative 1 minus n equals 0. So we could just simply add 1 minus n, and we have y equals 1 minus n. All right. And now that we have x, y, and z, we'll go back to our original form, and we see that the stopping time is m to the just m to the 1, that's m. Initial velocity to the y, that's 1 minus n. And b is to the negative 1. So we could just put b in the denominator here. All right, that's your stopping time. Now let's find the part B. So I'll say this is part A here, right? So now let's do part B. Part B is to get the stopping distance. Okay, so we're going to do the same thing. But this equation will look this equation will look the same. This side of the equation will look the same, but this one will look slightly different, right? Instead of t to the 1, we'll have t to the 0 and L to the 1. So m, x plus z. M to the x plus z. L to the y plus z times 1 minus n. And then t to the negative y plus z times n minus 2. That equals m to the 0, L to the 0, or sorry, L to the 1, and t to the 0. Right, because it's distance, okay? So again, x plus z equals 0, which means that x is negative z. y plus z times 1 minus n. Y plus z times 1 minus n. This equals 1. And negative y plus z times n minus 2 equals 0. So I'm going to add these equations again. So y minus y is 0. Z times 1 minus n plus z times n minus 2. 1 plus 0 is 1. And we'll distribute. So z minus zn plus zn minus twice z equals 1. Negative zn plus zn looks familiar. Z minus, okay, negative z equals 1. Z is negative 1 yet again. All right. But what is y? Yeah, y is slightly different now, right? So, y plus, so z is negative 1. Y plus negative 1, so that's negative 1 minus n equals 1. I can add the 1 minus n plus 1 minus n, and we can just remove the parentheses. 1 plus 1 is 2 minus n, right? So, yeah. So that's what y is, 2 minus n. And of course, x is 1 again, right? So I know that the stopping distance is going to be m to the 1. That's just m. And initial velocity to the 2 minus n. And then the b constant to the z being negative 1. I'm going to put that on the denominator. So it's pretty similar, but our initial velocities are different, right? Okay, now the second part of the question. Right, so we've been asked to see if our answers make sense, right? So let's see. Here's our stopping time. Does this make sense for a stopping time? Well, how do things look? Let's suppose n is 0. Then what do we have? We have that t is m v 1 minus 0, it's just v, over b, right? That seems fine. I don't know. So it says that if the mass is heavier, if the mass is greater, then it'll take longer for it to stop. That makes sense because of inertia. It has more inertia. And then it also says that if the initial speed is greater, it'll take longer to stop. That makes sense too. So far n equals 0 makes sense. I guess maybe n equals 1 doesn't make sense. This is 1 minus 1. That's 0. Okay. So yeah, that doesn't really make sense. It should really depend on the initial speed, shouldn't it? Let's keep going. This is 1 minus 2. That's negative 1. So that will be like something like this, right? This doesn't really make sense. This says that the greater the initial speed, the smaller the stopping time. But that doesn't make sense. It usually you would expect that if you have some damping oscillator, that the greater the initial speed that you give it, the longer it'll take to stop. That's just common intuition. So this doesn't make sense. And you see that if n equals 3, as you go up and up in n, this number actually becomes greater, and it makes even less and less sense, right? Because this will be a 2. Because why? Because 1 minus 3 is negative 2, right? So I'll take that out. So, there you go. See if your answers make sense. No, it doesn't. And now we'll look at the distance. Maybe, does that make sense? Let's suppose n equals 0. What's the distance? M. So this is the stopping distance, right? This is how much distance the oscillator moves until it finally comes to a stop. So for n equals 0, that makes sense. N equals 1. See, I don't know what n is, right? I don't know what physical significance m is. I just know that whatever it is, it's not making sense for when it goes higher and higher, right? So even though the stopping distance, if you just looked at this stopping distance, you would say, yeah, I mean, that makes sense. If the initial velocity increases, so should the distance, the stopping distance, right? And that makes sense. But then why would it get smaller? Why would that degree go smaller when n goes up? Well, I don't really know what n is, so. But all I know is that when n is when n is greater than 1, then now it doesn't depend at all on the, because 2 minus 2, right? Now it doesn't depend on all, and then n is 3, and we have v on the bottom again, right? And so we have the same problem. So this doesn't make sense. And the moral, I think the moral is that dimensional analysis is usually pretty good, usually pretty useful. But in some situations, it doesn't really make sense. Okay, those are the problems. Now we want to move on to exercises. So here we have exercise 1.8. Pendulum on the moon. All right, I'll let you see if you can solve this on your own. Cool, so now I'll provide a hint. If you recall from the example that we did, we found that the frequency of a pendulum was proportional to the square root of g. In other words, the frequency is equal to some constant times the square root of g. So if you apply some dimensional analysis on the frequency, we could deduce the proportionality between g and the period. Since the period has dimensions of time, is the reciprocal of the dimensions of frequency. So there's your hint. The period is 3 seconds, right? On the Earth, what would its period be? So this is Earth. On the moon, use the fact that g on m over g on Earth is 1/6. So why don't we do this, right? Why don't we find out the relationship between period and g? We know that the frequency was proportional to the square root of g, right? Frequency, the units of frequency, is 1 over time. That means that the period should be proportional to 1 over g, 1 over the square root of g. G to the minus 1/2. So the period on Earth is some number, right? Times g to the 1/2. Then the period on m, on the moon, lowercase m. The moon is not a proper noun. Is equal to the same constant as and times g on the moon to the 1/2. So what we can do is do Tm over Te, which is C Gm, do square root from here, GE. And so this is square root of GM over GE. This is the square root of 1/6. Okay. So TM over 3 seconds is the square root of 1/6. So TM is the square root of 1/6 times 3 seconds. Okay. So that makes about 1.22 seconds. Now again, I don't have an answer key here, right? So if I'm wrong, you know, if you know I'm wrong, why don't you leave a comment and you know, correct me, because it's better to spread correct information than incorrect information. 1.9 escape velocity. So here is the equation for escape velocity. Okay. G is our gravitational constant, m is the mass of the planet, and r is the radius of that planet. Write v in terms of the average mass density. So we need to write v in terms of rho, the average mass density, instead of m. All right, so I'll pause here and let you solve part A on your own, and then we'll do part A, and then we'll go to part B, and I'll let you solve part B on your own when we get there. Okay, now I'll provide a hint for part A. So they ask you to write V in terms of the density rho. They could be more specific here. They could say write it in terms of rho and G and R. So, right, so those can stay. Just that M is we can't use M anymore. So it's got to be, so V, we have to relate V to G, R, and rho. So that's your hint for part A. The units of M are mass, and the units of rho is mass over length cubed. The units of G is, as we've seen earlier, L cubed over mt squared. And the units of R is L. And the units of V is length over time. So how do we write this V in terms of the other R, G, and rho? So now let's see. Let's do what we've always been doing. Right? So we have R to the X, G to the Y, and rho to the Z. That's what our final answer will look like, right? So this is going to look like, if you write it in terms of the units, length to the X, you don't need the parentheses, length to the X, G, which is length cubed over mass time squared to the Y, and rho, which is mass over length squared, mass over length cubed, to the Z. This needs to look like length to the 1, time to the -1. So combine all these L's here. We have L to the X and then we times L to the, so that's going to be plus 3y, and then minus 3z. Okay, now if we do m's, oh, there's an m to the 0 here, by the way. Now if we do m's, we could do time. I mean, the order doesn't matter, but I'll do m. So we have m to the minus y and then plus z. Then we have t. This is going to be minus 2y, and that's it. This is going to be L to the 1, T to the minus 1, M to the 0. We can even, here, I'll rewrite it for this one, right? To the 0, T to the minus 1, okay? So that's going to be x plus 3y minus 3z equals 1. Then you have negative y plus z, negative y plus z equals 0. And then you have negative 2y equals negative 1. So y is a half. You can put y in here. Negative 1/2 plus z equals 0. Z is a half. And put a half and a half in for here. 3 or not 3. X plus 3 times a half minus 3 times a half equals 1. These cancel and x equals 1. So it looks like our result here, we can write that this is a velocity. Velocity should equal the escape velocity should be the radius of the Earth to the first power times g to the 1/2 power. I can write square root. And then times rho to the 1/2 power. Right? Because rho is to the z and z was 1/2. So. And we don't need the little one here. Get rid of that. Yeah, so that is my answer for this problem, at least part A. This is part A. Let's move on to part B, yes? Alright, now I'll let you attempt part B on your own, so go ahead and pause the video here and try that. Okay, now I'll provide a hint for part B. So, they provide the density of Earth in terms of the density of Jupiter, and the density of and the radius of Jupiter in terms of the radius of Earth. But we actually would prefer the two variables on one side to be in terms of the two variables on the other side. So what I mean is you would have to rewrite one of these in terms of the other one, right? So if you want, you can have Earth in terms of Earth in terms of Jupiter, or you can have Jupiter in terms of Earth. Okay, there's your hint. The average density of Earth is 4 times that of the average density of Jupiter, right? And the radius of Jupiter is 11 times the radius of Earth. What is the ratio VJ over V Earth? Well, can we just plug J in for these? So here's V, right? Here's V in general. In general, V is R times the square root of G rho. V is R times the square root of G rho. So V for J is R for J times G times rho for J. And V for E is R for E times the square root of G times rho for E. So RE, what's RE? It's RJ over 11. Square root of G, and then rho E is 4 rho J. 4 rho J, right? So this is going to be 2 RJ over 11 times the square root of G rho J. This is VE, right? So take VE. So we want VJ. Okay, VJ, that's fine. VJ over VE. VJ is RJ square root of G rho J. G rho J. And then VE is 2RJ. The 11 can come up here. And square root of G rho J. So G rho J, RJ, RJ. VJ over VE is 11 over 2. All right, I hope you enjoyed this episode of this lecture series that dealt with section 1.2. If you did, go ahead and drop a like. If you are digging this series, go ahead and subscribe. And if you have any questions, go ahead and comment. And if you dig my vibe and you would like some extra help with homework or your understanding or anything, a project, whatever you're doing, or if you want to prepare for a test, feel free to request my tutoring services. You can book a free 15-minute consultation with me. We can go over discounts, stuff like that. And I will also help you with whatever it is in that time, if I can. But yeah, regardless, thank you for watching. Peace out.